In class, we learned that many cycloalkanes have what's called ring strain because they're forced to have bond angles that are not ideal for sp3 hybridized carbons. However, cyclohexane is special. It's able to fold in a way that allows it to have the ideal bond angles of 109.5 degrees. In this video, we're going to discuss two of those conformations or folded structures of cyclohexane. The first of those structures is called a chair conformation. And you're going to want to get pretty good at drawing chairs in this class. They're going to come up a lot. And so the way I typically draw it is to draw two parallel lines apart from one another. And then I'm going to draw two more parallel lines sort of coming down diagonal away from them. And then I'm just going to connect the two ends. Like that. So remember, this is a line structure, so each one of those intersections represents a carbon, and so this is a cyclohexane. At that carbon, each has two hydrogens coming off of it. One of them is an axial hydrogen, which I'm going to draw in blue. I'm putting that break because that bond is at the back. And they each have an equatorial hydrogen as well. These are coming off not straight out, but a little bit out. The equatorial hydrogens on the end are a little bit easier to draw than the ones in the center. But this equatorial hydrogen ought to be parallel to this CC bond right beside it. And the same is true for this equatorial hydrogen. It ought to be parallel to that CC bond there. So, a couple of things to note. Every axial hydrogen is going either straight up or straight down. And it's going in the direction that the two carbon-carbon bonds are pointing. And so for this hydrogen, these two carbon-carbon bonds are pointing upwards, and so that hydrogen is going to go straight up. This axial hydrogen, the two carbon-carbon bonds are pointing down, and so this hydrogen is going to go straight down. And that's true for every axial position. The equatorial positions are always going to be going slightly up or slightly down, and it's always going to be opposite of the axial hydrogen that's on that carbon. So this hydrogen is going down, this hydrogen is going slightly up. This hydrogen, the axial hydrogen, is going up, so this equatorial hydrogen is going slightly down. If we want to think about the Newman projection of this chair structure, I'm going to look down this bond and this bond in this direction here. So I'm going to draw two circles right beside each other because I'm looking down two different bonds. And notice that in the front I have a carbon-carbon bond going up from this hydrogen. And so I'm going to draw that in here, and it's connected to that hydrogen. I've got a hydrogen going down on each of those carbons and a hydrogen going up on each of those carbons. if I go to the back carbon, so now I'm thinking about this carbon here, there's a hydrogen coming down and to the left, and there's a hydrogen going straight up. There's a carbon-carbon bond going down and to the right, and that's connected to the carbon that's behind this carbon here. Again, I've got a whole bunch of equatorial hydrogens connected there, and an axial hydrogen there. And so this carbon here is the same as that carbon, and this carbon is the same as that carbon. If I were to number my carbons, I could do that. This would be 1, 2, 3, 4, 5, 6. Carbon 1 is in the front here. Carbon 2 is directly behind carbon 1. Carbon 3 is this white carbon. Carbon 4 is in the back here. Carbon 5 is in front. And carbon 6 is up top. The chair conformation is the most stable conformation for a cyclohexane. It has another conformation called a boat conformation. This is going to be the least stable conformation of a cyclohexane. It looks a little bit like this. It's got 2 hydrogens coming off like that. These have an unfavorable interaction there. These are called a flagpole hydrogens. And these are coming down like this. And then each of these carbons has 2 hydrogens coming off of them. One going slightly down, one going slightly up. Or actually, most of them are going straight down, and then they have a couple going slightly up. If we look at the Newman projection of this conformation, I'm going to look this direction, down that bond, and then down this bond here. It looks a little bit like this. This time, this carbon is the same as that carbon. And notice the one in the back is also up. And so I'm going to draw this up like that. This carbon is the same as that red one. And that means that we've got some hydrogens going there and there. So if we look at this Newman projection, hopefully it's clear that this boat conformation is going to be way less stable than the chair conformation, because all of these are totally eclipsed structures. But over here, this is a staggered structure. There are a number of other conformations of cyclohexane, but these are going to be the 2 most important, as they're the most stable and least stable, and we're just not going to talk much about the others. Much like linear alkanes, the cyclohexane is constantly flipping and folding in different ways and moving. And I want to talk about the most common of these movements, and that's known as a chair flip. So the first thing I'm going to do is redraw my cyclohexane. I'm going to again start with my parallel lines. Draw two lines coming off of them, and then connect the two ends. The next thing I want to do is add my axial hydrogens. And so remember, axial hydrogens are the ones that are going straight up or straight down. And they always go in the direction that the two carbon-carbon bonds are pointing. And so this one's going up, that one's going up. And so the axial hydrogen is going to be going straight up from that one. If I look at this back carbon, the two carbon-carbon bonds coming towards it are pointing down. And so this axial hydrogen is going to be going straight down, as is this one. And this one will be going straight up. Then I want to take care of my equatorial hydrogens. Remember that they're going to be going slightly up or slightly down, and it's in the opposite direction of the axial hydrogen. And so this axial hydrogen is going up, so the equatorial hydrogen on that carbon is going to be going slightly down. This axial hydrogen is going down, and so the equatorial hydrogen on that carbon will be going slightly up. Like so. And that completes that. So what can happen is that this carbon can fold down, and then this carbon can fold up. So I'm going to take this one and sort of bring it down, and this one is going to come up. And so when that happens, this is constantly happening, so this is like an equilibrium reaction. And we have this carbon here is now pointing, has moved up. And this carbon has now moved down. So I'm going to make sure we note these two carbons. This was A, and so this is still A, and this is B, and this was B. What's important, however, to note when you undergo a chair flip is all the equatorial hydrogens and axial hydrogens switch. So anything that was an axial hydrogen in this molecule, once it undergoes this chair flip, is gonna become an equatorial hydrogen. And so all my red hydrogens are gonna be equatorial now. And all my green hydrogens are going to be axial. Notice still that if my two carbon-carbon bonds are pointing down, my green axial hydrogen now is also going down. And the equatorial hydrogen is going slightly up if the axial hydrogen is going down. That's going to wrap up this video. We'll continue with substituted alkanes in class next time we meet.